across the resistor.
Why is that V, or is it an R?
That's a V sub R.
V sub R. Alright.
Voltage across the resistor. It's supposed to be a lowercase v. So what this tells us is that if I just have a resistor there, that my phasor for the resistor is going to look like this. That is my resistor phasor for voltage.
The whole line
Spins
or
around.
Oh, the moving, like the arc?
Yeah, the yellow line is my voltage phasor for the resistor, and we'll call it red. Red line is the voltage phasor for the power supply.
The one going up or the whole thing?
The phasor is
Oh,
there like that.
Just that.
And I should label that. Of course, the change numbers. Now, the moral of this story is that the resistor phasor, actually, let's hold off on that. I know this is equal to IR. So the current going across the resistor is equal to epsilon sub naught over R sine of omega t plus phi. So I have a current across the resistor, or the maximum current across the resistor is epsilon sub naught over R. And so in my drawing here, if I were doing a proper phasor diagram, my axes, I have a phasor at some position. This is equal to epsilon sub naught and capital V sub R, because they're the same. And I have a current phasor, which also is completely in sync with it. It's still sine of omega t plus phi. And this would be the current coming out of the resistor, which is also the current from the power supply in this particular case.
Oh.
And now the moral of the lesson. For a resistor, the current phasor is in phase with the voltage phasor. The significance of this, unless you've done this before, I would assume is not hit you yet. In phase means that they lie on top of each other. Now, over there I drew my current phasor smaller than my voltage phasor. I didn't give enough information to really know which phasor. They're different units. You typically the second one I draw is the shorter one.
Question.
Yes.
Now for a problem besides this, would we be given a phasor like this and we have to figure things out from that? Or do we make a phasor at the end?
A typical problem is you're given the circuit and you have to figure out the phasor diagram.
So that's
Sorry, I
just like,
misunderstood.
no, that's fine. But it's like making a graph for the
Yeah.
circuit. Okay.
Yeah.
I
But
just
it
didn't
gets-
really understand what a phasor was.
A phasor diagram, a phasor is just a useful way of,
Sure.
of visualizing an AC circuit. There's a way with complex numbers, but 152 typically the phasor approach is the one that's taken. Other questions? Suppose I have a circuit with a capacitor. Again, I'm going to switch to cosine. Epsilon sub naught cosine of omega t plus phi.
Because it's a capacitor, or just?
Just because I probably should have done cosine before. It doesn't matter which one you do. The reason why is if it's cosine, then the projection onto this axis, well, in essence, the phase shift could just cause. So there.
So you can do both?
Yeah, either one.
You get the same answer?
Yeah. All right. So I know that I have some voltage going across the power supply minus the voltage across the capacitor. It's got to be equal to 0. So voltage across the power supply equals the voltage across the capacitor, which, well, I know that, it's flashback to DC stuff, I know capacitance is charge over voltage. So voltage would be charge over capacitance. I'll put a lowercase q since it's constantly changing over capacitance. So that is equal to epsilon sub naught cosine of omega t plus phi. So my charge, which is the change in current over the change in time. Nope, that is wrong. Let me back up. Let's keep it like this. Is equal to C, big C, epsilon sub naught, cosine omega t plus phi. I know that my current is equal, this is across the capacitor, is equal to the change in Q over the change in time, which is, well, these are constants for a problem, equal to the change in the cosine of omega t plus phi over change in time. So first off, what is the change in cosine over the change in time? It's still written over there. What is the change in cosine over the change in time?
Velocity?
Say it again?
Velocity?
No, I'm thinking of, that was just our entryway. From this right here, change in cosine over change in time.
Oh. Negative sign?
Negative sign. So that is equal to C epsilon sub naught, a little space there, sine negative omega t plus phi. You've already done that part. Now put a little gap right there, because there is one other impact, because here we were just starting with sine, we get to cosine and so forth, but that omega, what effect does the omega have? If this is sine of 2t, what would the slope look like?
It'd be 2 cosine 2t.
Say it again?
2 cosine 2t.
Now justification for that is that if sine of 2t, what that does is it shrinks the space in which it does this. It makes everything steeper. So it's now doing this. In the same 2 pi period, it goes twice. So it makes everything steeper, which means that the slope would be steeper. And so if you have an omega there, all that does, that basically you just multiply that out. Another way of looking at it is that if we think of this in terms of angular frequency or angular speed, it's going twice as fast as before, which means that my changes are twice as much. So there's an omega that pops out here. The phase shift doesn't change any steepness, all it does is just shift the entire graph left or right. So if I plotted out my cosine and sine curve, because my EMF is a cosine, my voltage for the capacitor is also a cosine, but the current is a sine. So my phasor is not going to be over top of each other. If I plot a sine curve, it looks like that. If I plot a cosine curve, cosine looks like that. They are out of phase. Matter of fact, the sine curve is ahead of the cosine curve. This is my sine curve here. And this distance right here is 90 degrees, pi over 2 radians. So my phasor diagram, I have my voltage phasor for the power supply. It is also equal to my voltage phasor for the capacitor. But my current phasor, let's see, so I started out with that as a cosine. My current phasor leads.
So it'd just be a reflection over the y-axis? No.
That is the current of the capacitor, the current phasor.
Just 90 degrees after it?
That's 90 degrees.
Is it always going to be current first, or does it change?
Current is always going to, for a capacitor, is always going to lead the voltage for that capacitor. So for a capacitor, again, these things are spinning around counterclockwise. For a capacitor, the current is ahead of the voltage. For an inductor, which one do you think leads? Gut feeling.
Alright.
So the same
No, the other one.
voltage?
Yes.
And who did I say was coming soon?
Eli Manning.
So for a capacitor, the current leads. For an inductor, the voltage leads. Now I have an E here, so I have an epsilon. This comes back to engineering textbooks tend to use the letter E for voltage. Of course that's not going to be confusing with energy or anything else like that. Because my take on it is that they want to do an epsilon, but before you really had computer graphics and you were setting this up by hand, doing an epsilon was not necessarily easy, and so they just went to the capital E for voltage. So if you're running across capital E for voltage, that's in essence where it comes from. It's bastardization of the epsilon. So anyway, time is up. Good day. I said good day. and have a nice weekend.